All right, this reaction is a reaction between vinegar, which is acetic acid, and baking soda, which is sodium bicarbonate. The first thing that you'll notice is there is some vinegar placed inside of this glass vial. And to the vinegar, I will be adding some baking soda using a spoon. And when the baking soda is added, you'll see that a chemical reaction occurs. In this chemical reaction, you will see a foaming, bubbly product. So you can see that it flowed over. What's happening is that this double replacement reaction, the sodium and the hydrogen, the sodium from the sodium bicarbonate and the hydrogen from the acetic acid are going to switch places. And that is why it's called a double replacement reaction. And you can see on the product side that the sodium and hydrogen have indeed switched places. Now, there's also H2CO3, and that is very unstable. So let's watch what happens as soon as this double replacement has occurred. Note the bubbles. That means a gas has evolved. That is carbon dioxide gas. And what happened is that carbonic acid is what it's called, has created carbon dioxide, and that can be proven by showing a lit match being placed into the tube is put out because there's no oxygen. So here's the reaction. We have the carbonic acid, which is H2CO3, is decomposing, because it's unstable, into water and carbon dioxide. The water you could see because of the liquid that was in the tube, carbon dioxide. We showed it when I demonstrated that the light went out. Okay, so these represent hydrogens, and hydrogen is never by itself. It's always with another hydrogen because it's diatomic. And hydrogen reacts with oxygen, and oxygen is diatomic as well. It will never be by itself. So here I have hydrogen plus oxygen, and what I'm going to form is water. So water requires 2H2 and 1O. Okay, but I still have leftover oxygen right here. So what I'm going to have to do is add more hydrogen. And so then those two will react to form a second water. So to summarize, we had 2H2 plus 1O2 yields 2H2O. This is a synthesis reaction. Two things react to become one. Have the reaction of a hydrocarbon, and in the case of this reaction, it is methane, which is CH4. It's a hydrocarbon. Burning, which means that it's an oxygen, and always produces CO2 and H2O. To balance, simply look at the numbers of each of the elements. 4 hydrogens, put a 2 in front, that balances. There are 4 oxygens on the right, and now that one's balanced if you put the 2. The next type of reaction is a decomposition reaction. In a decomposition reaction, one thing, one compound becomes two or more. And so a nice example is right here. We have an egg that when it hatches produces a chick. So this would be like saying A, B breaks down to form A plus B. An example of a decomposition reaction is the reaction of potassium chlorate, KClO3, to form potassium chloride and oxygen. Now, oxygen's a gas, oxygen's diatomic, so we always have to have that 2 there. So, this is the reaction because a decomposition reaction because one thing that could be our AB is breaking down into 2. Now, the only thing that we have to do still is balance this reaction. So let's start by looking at the potassiums. There's one here and there's one here. Those are balanced. Chlorine, one here, one here. Those are balanced. Oxygen, there's 2 and 3 on this side. So in order to balance the oxygens out, you're going to have to take the potassium chlorate and put a 2 in front of it so that the 2 times 3 equals 6. And you're going to put a 3 in front of the oxygen, so 3 times 2 equals 6. Now, in doing that, we also have the issue now that our potassium and chlorine, there are 2 of them, whereas before there was only 1. Therefore, we will have to put a 2 in front of the KCl as well. And now we have 2 potassium, 2 chlorine, 2 potassium, 2 chlorine, and 6 oxygens, and it is balanced. And I'm going to rewrite it just because I want it to be separate and clear. And so I'm going to write 2KClO3 breaks down to form 2KCl plus 3O2. That is decomposition.
Many chemical reactions are exothermic, but none quite like the thermite reaction. Here we have a piece of filter paper which we're going to fold into a cone. We're going to place a mixture of aluminum and iron oxide into the cone. We're also going to add some thermite starting mixture. This is a powdered material which helps the oxidation reaction. We're going to place that then in a hole in this container of sand. I'm then going to place a piece of magnesium ribbon down into the mixture and move the explosion shield into place before we light the magnesium fuse. Now we can take a look at the molten metal by carefully lifting it out of the sand. This white-hot iron is encased in a crucible of glass that has been made by melting the sand. You can see some of the liquid metal as it dripped out of the glass. We're going to allow that to cool down, and then we'll chip some of the ceramic off the metal and take a look at it. Let's now use a hammer to crack off some of that ceramic. Here we see some of the crude ceramic that enclosed the metal. And here we see the metal, the pure iron that forms. Let's take a look at the chemical equation for this dramatic reaction. Here we see that the iron oxide is reacting with the aluminum in a single displacement reaction. The aluminum oxide is produced, and there's the iron metal that you saw in the molten state. And of course, a large amount of energy in the form of heat and light was released.